the degeneration of Gelfand-Cetlin system, which was constructed by and first, for application, I'd like to modify the construction of the toric degeneration. In the last two lectures, we constructed those data. This is the degeneration of Gelfand-Cetlin system. With chi is gamma delta. Gamma is a path. It was a piecewise linear path to the complex vector space or affine space, and tilde was a family the generic fibers are flag varieties, and a special fiber, central fiber, X0 was a Gelfand-Cetlin toric variety. And omega tilde can be considered as a Kerr form on the total space. And this is given by the restriction of some constant multiples of Fubini-Study Kerr form of the sum of constant recall that the flag manifolds are embedded in the product of projective spaces. And tilde is a family of momentum maps. It is basically, it is a priori a map to the real space, but the image is always the Gelfand-Cetlin polytope. And finally, the
so I feel like depend on the restriction on the curve. Restriction of the curve.
Yeah. Okay. We consider we restrict the family of the piecewise linear path, and this is the family. And phi, maybe phi tau is a map from T prime to T prime minus T. This is a Hamiltonian gradient Hamiltonian flow. Okay, then the path was such that the path goes starting from the points or coordinates 1 and go to the point. The final coordinate is 0. And next, then, and goes piecewise linearly, and finally go to the origin. In this, we consider the family over this path, and there is some defect in this construction when we consider the application of this construction. Is that the fiber over gamma t is usually singular. Namely, after the point, when we pass this point, the fibers of this system or of this family is usually singular, except when this the starting Planck manifold. Sorry, x1 is a Planck manifold, x gamma 1, x gamma x1 1 of the Planck manifold. This is except when that is already toric, always singularity appears. So, for applications, we want another degeneration. So that only the fiber of gamma, only the fiber over 0, 0, 0 is singular.
Cannot path. Cannot path. Path.
Real path.
Hmm?
Gamma is real path.
Gamma is path. Yeah.
Okay, so then what is the notation on the top?
Gamma goes from this point and straightly this point and so on.
So are they different then?
Hmm?
Path from that point to that point.
Yeah.
I see.
Starting from.
Sort of composition.
Yeah.
Right.
Okay. For this purpose, we consider another path. The family passes, in fact. We consider the following family passes. Take passes. The passes approximating. Namely, we consider the following. Maybe this is yes. Gamma S starts from the same point and go to the coordinate where the last coordinate is S, and then and so on, and finally reach to the point all the coordinates are S. And we can also consider the gradient. We can consider the gradient Hamiltonian flow along this path. And we call this phi s. This diffeomorphism as phi s, which sends x111 to x SS. Then move s from 1 to near 0. We have we again have a family of diffeomorphisms. We have a family of and this gives the phi tau. Okay. Family of diffeomorphisms over the path gamma dash from going from 1 to 1 0 0.
Excuse me. What is the gradient Hamilton flow in this?
Gradient Hamilton flow. This was defined by Ohara, and if you have a family function or function or holomorphic function or family over the complex plane, then the what was that definition? The Hamiltonian vector field. Yeah, what was that? I don't remember the definition. And C equal minus lambda real, yeah. Blah, blah, blah. Is that correct?
Left hand side should be divided by small square. Left hand side is also divided by small square.
Okay. Yeah. This is the same definition as Nohara's. Then, a priori, this is defined. This is not precise in strict sense. It is defined non-zero. Only the point it is non-zero. Okay, do you see what I mean? So there's 1 1 1, and here is 0 0 0. This family is diffeomorphism over this, not containing this, but we can show that Type psi is extended to a map phi, which is a map from 1, 1, 1 to 0, 0, 0. So this is this map is not a diffeomorphism because these are clearly not diffeomorphic manifolds, but we can extend the family of diffeomorphism to the limit, and we can also show that the okay, or we can also show the momentum maps is 0. It's bounded by for note that the phi 1 was a map from x1, which is a Flach variety, to the momentum polytope, and from this psi s maps this to xSSS, and then go by phi s maps this to phi 0. And phi 1, phi 0 is a momentum map on this singular Toric variety, and this commutes. So this states that this almost commutes, and the order of commutativity is gets better when when s gets smaller. This constant doesn't depend on s.
What's phi s?
Hmm?
Phi of s?
Phi s is a Hamiltonian gradient flow. Hamiltonian gradient flow of from here to here. This is different from the Noether's. And so in the limit case, taking the limit, in the limit, in the s goes to 0, we also have a map phi, then phi 1 equals phi 0 and psi. This means that this is almost the definition of means that we have degeneration of Gelfand-Cetlin system. Meaning that the integral system.
But could you explain the map on the bottom?
On the bottom.
Right.
And this is somewhat vague statement. This is a map. And this both.
So is this distance or
Yeah. Distance in this space. I don't write explicitly, but in appropriate sense. Okay. So
psi in that box is a limit.
Yeah. In this way, we have a family over this. Not the first construction was going the other way and go in piecewise linearly, and the first family becomes singular after this. But this family is constructed on this line, and on this line, the variety is smooth, except this central fiber. But still, we have a commutativity of degeneration and integral system. So
the map you consider is a limit, or before you take the limit? Is it, are you going to consider the maps psi after you take the limit s goes to 0, or
psi is itself defined as a limit. We have a family of maps, this one, and we can show that this family converges to some map, and this is the limit. Okay. And summarizing, we have obtained Toric degeneration of Gelfand-Cetlin system over this straight line. And the points are that the integral system. Integral systems are given by the push forward Gelfand-Cetlin system. Note that this statement is vacuous for except for the origin, because we a priori don't have a natural definition of integral system over these fibers. Only this and this this point has a Gelfand-Cetlin integral system, and this has a Toric integral system. That statement says that pushing forward by this diffeomorphism, the Gelfand-Cetlin system converge to the Toric integral system. And this is that statement is equivalent to this. And the complex structure. Complex structures are given by a restriction connection as a subvariety. Subvarieties. The product of projected spaces. We push forward the integral system, but complex structures are the restriction of the given complex structure, not the push forward. This is the part.
How do you push forward Gelfand-Cetlin system?
And just it is a diffeomorphism preserving a simplex structure. So just map the fiber to fiber. Yes.
It doesn't become singular? Like, at the end of...
At the end, the yeah, at the end, yeah, it combined the general fibers are still still like the torus, and okay.
Yeah, maybe I'm confused. So you have this SSSSS,
Mhm.
00000, but after you, but from here to here, at 0 there is a singular
yeah,
point
yeah,
in the fiber.
yeah,
But you're pushing
the,
for, there's an integral system here
Mhm.
at SSSSS,
Mhm.
and you're pushing this to
Mhm.
0 fiber.
Mhm. yeah,
By pushing, you mean there is this integral functions.
yeah. Maybe precisely speaking of the central fiber, we push for the integral system in the open-dense part.
When you push forward, do you use Hamiltonian diffeomorphism or
Yeah. No,
Sibylec morphism or Hamiltonian?
we push forward by this. Yeah, this is this preserves the simplex structure.
Only
Yeah.
individual so simplex.
Yeah. Yeah, preserve the simplex form.
Fiber-wise, it's effective morphism.
Mm.
Fiber-wise.
Fiber-wise.
But not it's not a, how to say, globalist.
Globally,
Not, it's not.
yeah. Then we use this from this xt for t small is close to x0, both has complex variety and integral system. Having this, we can use the results of x0. This is the toric case. It is well studied to investigate xt. This is the Flagg manifold. And this is the purpose of the rest of my talk. Yeah, this kind. Yeah. Okay, then. As an application of this construction designation, we analyze the modular space of Hom disks in Flagg manifolds using the results in the case of toric variety.
Can you give us some structures from X tilde?
X tilde. This one.
Yeah.
Sorry, what the question?
Because family, right? On the family.
No.
We had family of like manifold.
Yeah.
Yeah. So on that, do you have some structures like for you? What I'm saying is like when you deform like associative algebra, then on the family, family itself is kind of associative algebra.
The simplex structure.
In this case, you only
integral structure.
consider only like each kind of
Yeah. But the integral structure is pushing forward, defined by pushing forward. So we can think every fiber we have the same thing as a.
But as deformation, then we have to consider the whole family.
Holomorphic structure is also not. There is no local deformation of holomorphic structure on fragments. So
really, your ambient space X tilde going to be just a Keller manifold work, right? It's going to be just Keller manifold, Keller.
Yeah. Yeah, this is a.
That's one of the requirements, right? That's one of the requirements. You like impose. That's one of the conditions you like impose.
Yeah. This is a family of Keller manifolds. But what appears in the end is only depends on the simplex nature, like Fourier theory, because we are considering Fourier theory. So there's no, essentially, there's no.
So if you have a Keller form, then it is Keller manifold, right? Keller form. Yeah, so define the Keller form as the sum of the forms on like this P and K, right?
Yeah.
Right.
Still there is a sub-variety of the product of positive space times C n minus 1.
Yeah.
So we can use the natural Keller form on that space.
Is it okay? So, it's again. Again, let this data be a Toric degeneration of Planck manifolds and degeneration of Gelfand-Cetlin system. And we want to use the results of Choano on holomorphic disks on smooth Toric varieties using this idea. But the problem is that is that x0 is singular. So it's seemingly it causes a problem because this analysis, this study was done on smooth Toric varieties, but this, as Nohara mentioned, has small resolution. We write it as x0 tilde to x0. And this x space, the small means that the inverse image of singular points of x0 has codimension larger or equal than 2. So, using this, we can resolve the problem of singularity.
X0 tilde is still correct.
Yes. Actually, we will prove those two lemmas. First, the homotopy groups. Oh, no. Naturally isomorphic. Secondly, holomorphic. Second lemma concern about the holomorphic disks in the central fiber intersecting the singular locus. And the claim is that these disks always deformed into Torically transverse. We define this.
Always this is small resolution.
Sorry?
Always this is small resolution.
No. In this particular case of degeneration flag varieties.
In that case,
Yeah.
how can you draw the picture for small resolution? Do you add some?
One construction gave by Nohara. He explicitly constructed small resolution.
Vibration over P1. So I iterated vibration structure on P1. So first we degenerate. At the first stage we construct a n-1 flag over n flag for n-1. We have vibration of fiber P1 to n-1. And we again degenerate the smaller flag into a next end of the next stage. And then we go.
Maybe there is a simpler construction that the toric variety is defined by fans.
So can you explain from the pen picture?
For three-dimensional cases.
But
we just add a X to
the small resolution is defined by the refinement of the fan without adjoining edge, one-dimensional edge, and this can be done pictorially in this.
Not edge. What do we add?
Edge is none of that.
Face.
Face, just face.
Okay, then torically transverse. Maybe stable map. A stable map is a map, holometric map without any continuous automorphism. Okay, is torically transverse. If the first condition is that the image doesn't intersect the toric strata of a larger codimension. And secondly, the inverse image of the interior part of X0 means that the X0 minus the toric divisors is dense in sigma. These are conditions for torically transversality. In our case, the important condition is here, and this means that the image of this map P doesn't intersect the singular locus, because singular locus lies on codimension moreover to part of X0.
Here, deformation is algebraic.
Firstly, we are considering a disk, so but yeah, actually, we can analytically continuous disks to close the curve, and then the deformation is arbitrary. Yeah, can be algebraic, but we don't need the algebraicity for construction. Okay, then we prove these lemmas. First, the second homotopy group of toric variety is generated by toric strata, and we write them by SI. And if X0 tilde, X0 is a small rejection, for any I, there is a toric strata of X0 tilde, and then toric of X0 tilde, such that, sorry, this maybe pi, such that the image of this strata is the toric strata on the original X0. This follows from the, for example, from the construction of the X0 by the fan picture. And since x0 tilde is smooth, xi tilde can be deformed smoothly in the smooth sense, not algebraic deformed, so that it does not intersect the exceptional locus of x0 tilde. And this is because the resolution is small, and the exceptional locus has a real coordination more than or equal to 4, and this is 2 dimension. So this can be homotopically deformed, so that disjoint from the exceptional locus. And let xi tilde prime be the deformed curve. Then the image by the projection or by the projection of Si tilde prime doesn't intersect by the singular locus of x0. And note that the map from maybe this is 1 minus t. This maps x0 is a diffeomorphism. Except the singular locus of x0. This Si prime can be pulled back to xt, and obviously the homotopy class of this Si prime equals Si. This class comes from the lift of this class comes from a sphere in xt, and this proves the surjectivity of the map. The surjectivity of x0 xt to y2 of x0 is may be given by 5 minus 1. Okay, and so the rest of the problem is the injectivity of this map. We are going to prove this, and on the other hand, pi to xt, this was a flag manifold, is generated by holomorphic spheres, rational spheres, rational curves. sorry. For example, it is realized as a Schubert variety, and take homotopically different cycles phi 1 pi this maybe ti goes to 0. With the homotopy class is fixed. Note that xt for different t, unless this is 0, is naturally diffeomorphic, and we can identify the homotopy groups of these 4 different t. And we take homotopically different holomorphic cycles using this fact. In homotopically different cycles, when ti becomes going near 0. And using Gromov compactness, we can assume there is a limit. There are limit curves. P1 prime and P2 prime. This maps unknown. Maybe this is the union of spheres. Okay. I see. Maybe different region. Or sorry, one. Then this is using small resolution. Oh, sorry. And assume that, and assume the homotopy classes of the limit curves are same in by 0. But using similar resolution, we can, as above, we can remove phi1 prime, phi2 prime, both, so that they don't intersect the singular locus. So lift to the flag manifolds. But we started from phi 1t and phi 2t, and the homotopy classes are different, and we go to the limit curve. And this, we assume that this is the same. Sorry. And we denote the lift. We denote the lifts by phi 1 t prime phi 2 prime, and the lifts, because phi 1 prime and phi 2 prime are assumed to be giving the same homotopy class, so the lifts are also giving the same homotopy class. And by construction, these are the same. But this was not the same, so this is contradiction. And because this group is generated by those holomorphic curves, it follows from this that the injectivity of pi 2 xt pi 2 x0 okay.
Here, there's no relation to x0 tilde and xt.
X
Tilde and xt.
x0 tilde and xt. Or homotopy groups of, or what?
How they are not related. X0 tilde is the resolution, xt is the definition.
I don't know the.
Same away from, far away from exact numbers.
Yeah. Yeah, it's not the deformation of or
But it might have different topology of x0 tilde and xt.
the tilde different, topologically different. Xt is a smoothing, and x0 tilde is a resolution.
How about the highest layers? How about the high homotopy group?
I don't know, because the smallness only maybe up to 3-dimensional homotopy group, but we can make this lifting construction when the cycles are 3-dimensional.
But you only test the pi 2. You try to count like this.
Yeah. And what we need is only pi 2.
Maybe this is a stupid answer, but maybe if the resolution is the covering, then the higher homotopies are the same.
Yeah. But it only happens when x0 is itself smooth.
It's not really vibration. We have like singularity then, obviously. But how the jump is like, it looks like jump is only one-dimensional things, so that's
Right.
pi 2 means like there is like no big jumping at singularity, like
think the point is in Toric variety, singular locus is codimension at least.
At
Complex
least
codimension 2. At least complex codimension 2. So pi 2 can't really see the singularity. But if you think of a pi 4, yeah, higher things might intersect this singularity, which is complex codimension 2. So that's why, even though you take resolution, it might still intersect this exceptional. I mean, by generic perturbation, it still intersects this exceptional thing.
Okay, then we'll start from the proof of lemma 2 in the next lecture.
브레이크하고